Few more methods to solve systems of differential equation. I'm going to start with the Laplace transform. We're going to go back to Laplace transforms, okay? And I mean, all you need to recall about it is, well, the Laplace transform of the derivative and the Laplace transform of potentially the second derivative and derivative. So the advantage of solving systems using the Laplace transform is that we can solve systems of not just order one, order two, higher order, which we didn't do with eigenvalues and eigenvectors. Eigenvalues and eigenvectors are only useful for now for first order and systems of n differential equation. Okay, how do we do the Laplace transform for a system? Okay, well, take the Laplace transform of the first differential equation, take the Laplace transform of the second differential equation, keeping in mind the initial conditions, Okay, so that is, take the Laplace of dx dt equals the Laplace of 3x plus 4y. And notice how this system right here looks exactly like the ones we did with eigenvalues and eigenvectors. And then take the Laplace dy dt equals the Laplace of negative 4x minus 3y. All right? Okay, the Laplace of the derivative, be careful, because now we're going to use two different variables to denote. Okay, this is going to be some s x of s minus f of x of 0 in this case, equal to the Laplace transform of 3x. This is simply 3 times x of s. The Laplace transform of 4y, that's simply 4 y of s. Now for the second equation, the Laplace transform of the first derivative, but this time of y with respect to t, that'll be s y of s minus y of 0 equals to, what is that? Negative 4 x of s plus, or rather minus, 3 y of s. Okay? And we're done taking the Laplace transform, don't we? Okay, now let's substitute the initial conditions here. So, what is x of 0 equal to? Isn't that equal to 2? And what about y of 0? Isn't that equal to 1? Okay, so let's keep writing this. Let's keep going. So this will be, and keep writing the system equation, the system notation. So this would be s x of s minus 2 equals to 3 x of s plus 4 y of s. And then s y of s minus 1 equals to negative 4 x of s minus 3 y of s. All right? In this case, guys, what are the unknowns in the system of equations? The function f of x, and the function x of s and the function y of s. Just like x and y, right? Like in any regular system of equations. It's just that these are functions of s. So how about we move the unknown functions to the left-hand side and and everything else to the right hand side. Okay, and the constants to the right hand side. That'll be the following. Check this out. So this would be s x of s. Okay, I'm going to move the 3x of s to the left minus 3 x of s. This negative 2, I'm going to I'm going to move it to the right hand side with the opposite sign. And also, well, I'm going to move the negative 4y of s, and that equals to 2. And same here. These terms containing x of s and y of s, I'm going to move them to the left-hand side of the equation. And this negative one, I'm going to move it to the right. That is s y of s minus 3 y of s minus 4 x of s equals to 1. All right? Did you guys agree? Common terms in the first equation, the x of s, yes. Oh, yes, plus 4x, right? Both of them, right? Yes, thank you. Thank you. Good catch. All right. Well, let me factor x of s in the first equation. That'll give us, guess what? S minus 3, x of s minus 4, y of s equals to 2. And likewise, s plus 3 times y of s plus 4. Oh, this is x of s, not x of x, right? Oh, come on. Yes. Okay. 4 x of s. But do you know what, guys? I think I'd rather have. Okay, let me write the y term afterwards. Let me write the x term first. Okay. So otherwise, this could be a good place to make mistakes, which you don't want to. Okay. So guys, that's the system of equations we need to solve. And well, we could do an elimination, we can do a substitution, but you know what I'm going to use? I'm going to use Cramer's rule using determinants, okay? So for this, well, again, these are the unknowns, okay? Let me highlight the unknowns. That is, this is the unknown, this is x, and again, oh shit, I did x of s. Yeah, right? And y of s, y of s. These are the variables, okay? So for Cramer's rule, we need to calculate some delta. That is the determinant of all the coefficients of x and y. That is s minus 3, 4, and negative 4, s plus 3. Let's evaluate this determinant. S minus 3 times s plus 3 minus minus is plus 16. But isn't that the factor form of a difference of squares? All right, isn't it? So this is equal to s squared minus 9 plus 16, which is, what is that? S squared plus 7. Okay? Okay, let me calculate delta x. What is delta x? Delta x is it's calculated by replacing the column of the x's in the delta with the constant terms on the right of the equation. Okay, so that is, I'm going to replace 2 and 1 and negative 4, s plus 3, that remains the same. Evaluate the determinant. 2 times s plus 3, that is 2 times s plus 3. Minus minus is actually plus 4 times 1, which is 4, which is, that is 2s plus 6 plus 4, which is 2s plus 10. Okay? All right. What about delta y? For delta y, that equals, okay, for the matrix delta with the coefficient matrix, which has the entries with the coefficient matrix, I'm going to replace the y column with the constant terms on the right hand side of the system, keeping the x column the same, s minus 3 and 4, and evaluate the determinant. All right? What do we do? S minus 3 times 1, which is s minus 3. I'm going to do that times 1. Why not? Okay. Minus 2 times 4, which is 8. Okay. Let me do the 2 times 4 so you can see where it's coming from. That is this one. So s minus 3 minus 8 equals s minus 11. All right. So we have everything we need to find the solution to the system. But well, that's just the x of s. All right. Okay, let's go to the back side of the page, I guess. Uh, so to calculate x of s, we always divide the delta x divided by the delta itself. That is, what's delta x? 2s plus 10. What was delta itself? S squared plus 7, isn't it? And What is this? Isn't that the same as saying uh, 2s over s squared plus 7 plus 10 over s squared plus 7? All right? We can just split the fractions. Okay, guys, how do we get this? Is a function of s still. We need to retrieve the function of t. What do we do? Inverse Laplace transform, all right? So what do we do? Laplace inverse of x of s equals 2 times the inverse Laplace transform of s over s squared plus 7 plus the inverse Laplace transform, or 10 times the inverse Laplace transform of 1 over s squared plus 7. Okay? The first inverse transform takes us to, where does that take us to? Cosine, isn't it? So that is now x of t equals to 2 cosine of, what is that? Root of 7 times t? What about plus 10 inverse transform of 1 over s squared plus 7? However, However, didn't we wish we had a root of 7? We can make our wish come true, provided we divide out. Again, we're going to make wishes come true back, all right? We haven't done that in a while, right? That is plus 10 over root of 7 sine root of 7 times t. So that's the solution for the x part. What about the y part? Similarly, the y part, the y of s, equals to, what is that? Okay, delta y this time over delta, where, what was delta y? That was s over 11, s minus 11. And what was delta? S squared plus 7. Split it. S over s squared plus 7 minus 11 over s squared plus 7. All right? Okay. So, yeah, same, inverse. Inverse Laplace of y of s. That's going to give us our y of t, isn't it? So, okay, inverse Laplace of s over s squared plus 7 minus 11 inverse Laplace of 1 over s squared plus 7. Okay, the first one again, that's cosine of square root of 7 times t minus, oh, again, we need to make our wish come true. Multiply by a root of 7, divide by root of 7. Okay. And that's going to leave us with, what is that? 11 over root of 7 sine of root of 7t. All right. So that's the solution to the system. This is the x equation, and this is the y equation. All right. No eigenvalues, no eigenvectors, only a tool that you already know how to use, Laplace transforms. That's all it is. All right. Okay. So let's see about it. Let's have a look at the next exercise. I don't think I'm gonna get the chance to finish the whole thing, but at least I'll try to get somewhere. Okay. So, all right. So take the Laplace transform of the first equation, the Laplace transform of the second equation. All right. Let's see how far can we get in the last few minutes. Okay. So on the one hand, we get s x of s plus 3 times x of s as well, plus y of s equals the Laplace transform of 1, which is 1 over s, isn't it? And what else? The Laplace transform of the second equation, yes. Oh, yes, thank you, thank you. I don't know why I do that. Thank you, thank you. Plus x of 0, thank you. All right. And then the Laplace transform again of x of the derivative. And I also forgot, yeah, that of y, right? Thank you. Yeah. plus y of 0. Okay, good catch. So again, s x of s plus x of 0, don't forget it, plus minus the Laplace transform of x, which is minus, oh, cool, that is can, no, minus x, no, that's x of 0 here, minus x of s, all right? Plus the transform of the derivative of the y function, that is y of y, sy of s. Oh, shoot, this should have been sy of s, right? Sy of s minus y of 0. Sorry about that, okay? I corrected it. Minus another y of s, okay? Oh, I'm gonna need some space in here, all right? And that equals the Laplace transform of e to the t, which is what? Isn't that 1 over s minus 1? Okay. All right, well, let's move terms. Wait. Substitute the conditions. That is x of 0, which is 0, great. Y of 0, which is 0, that's also great. It's great that these are all zeros, right? That reduce the amount of terms. All right. Okay, guys. So that'll be equal to, that reduces to, okay, s x of s plus 3x of s plus s y of s equals to 1 over s. And s x of s minus x of s plus s y of s minus y of s equals to 1 over s minus 1. All right? Okay, let's combine rather factor, So let's write the system in a factored form. That is s plus 3 x of s plus s y of s equals to 1 over s. And the second equation becomes, by factoring x of s, that is s minus 1 x of s plus s y of s equals, what is that? 1 over s minus 1. All right. Well, so that'll be the system to actually, yes. Y of s where at the end of the set. Oh, yeah, yeah, yeah. So that's actually an s minus 1, right? So plus s minus 1. Thank you. So that's the system to solve, where the unknowns are x of s and y of s, and then find their inverses. Okay, yeah. Let me at least do the delta. So the delta would be s plus 3, s minus 1, s minus 1. All right? So this would be s plus 3 times s minus 1 minus s times s minus 1. Yeah, there's some algebra involved in here. But actually, instead of doing all the foiling here, check this out. I'm going to factor s minus 1. And that'll leave me with s plus 3 minus s, which is going to leave me with s minus 1 times, cancel the s's, times actually 3. Otherwise, FOIL and cancel terms. That's fine. But I'm just going to do this trick. One more minute. So the delta x will be given by, what is that? I'm going to replace the x column with 1 over s and 1 over s minus 1, s and s minus 1. All right? That is s minus 1 over s, multiply these two, minus s times s minus 1. Okay? All right, guys, let me at least show you one of the calculations here, because guess what? We need to multiply here by s minus 1 over s minus 1 and multiply by s divided by s. This to get s minus 1 squared minus s squared divided by s times s minus 1. All right? And what's next? The next one would be to, let me expand the binomial. That's s squared minus 2s plus 1 minus s squared over s times s minus 1. All right, which reduces to, what is that going to be? Reduces to 1 minus 2s over s times s minus 1. And guess what, guys? You would need to use partial fraction decomposition for this. Okay? Use partial fraction decomposition. Well, no, not yet. Not at this point. Let me at least set up just give me a couple minutes. Let me do x of s. Okay, x of s. Bless you. That is delta x over delta. And then, well, I'll let you do the other one, okay? So that'll be delta x, which is 1 minus 2s over s times s minus 1 divided by delta, which is 3, okay, times s minus 1. But let me divide this by 1 so we can multiply by the reciprocal. This would be 1 minus 2s over s times s minus 1, all right? And that times 3 or 1 over 3 times s minus 1. All right? Combine these together, x of s, that is 1 minus 2s over s times s oh, no, 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 3, s minus 1 quantity squared. Okay? After doing partial fraction decomposition, which I'm going to skip, you should get negative 1/3 over s plus 1 over 3 plus 1/3 over s minus 1 plus 4/3 over s minus 1 squared. And seems like you did a couple of mistakes in here. I forgot to this factor of s in the denominator of the fraction for x of s. Also, I got the wrong coefficients of the part of the partial fraction decomposition part. This should have been 1/3 plus negative 1/3 and another negative 1/3. All right, well, let's take the inverse transform to finally find the solution and obtain, at least for now, the solution for the x function, okay, the x of t function. So that'll be equals to 1/3 the inverse transform of 1 over s plus negative 1/3, which is minus 1/3 the inverse transform of 1 over s minus 1 plus another negative minus 1/3 inverse transform of, okay, did you see this s minus 1 squared? Actually, that should remind us of the first shifting theorem, which is 1 over s with s going to s minus 1. This shifting factor will mean e to the t, a factor of e to the t upon performing the inverse transform using the inverse form of the first translation theorem. All right, well, so finding the inverses, so the inverse of x of s, this would have been x of s, since it's now x of t, of course. That'll be 1/3 times the inverse transform of 1 over s, which is just 1. That's a transform of 1, minus 1/3 the inverse transform of e of 1 over s minus 1, which is e to the t, and minus 1/3 the inverse transform of 1 over s. Oh, actually, this is a squared one, right? Because of squared right here. Forgot that squared. And that'll be the inverse of 1 over s squared, which is t. But because of the shifting, gets multiplied by e to the t. All right. And that is the x solution. So now we need to find the y solution. Okay, guys, before getting into the inverse for the y, uh, notice at one point did we actually perform the partial fraction decomposition. So I know you're doing the deltas and you're getting fractions, so do not do the partial fractions in the deltas. Wait until you find the quotient delta x over delta y or delta y over delta, or delta x over delta or delta y over delta, because otherwise you would be doing a lot of unnecessary partial fraction decomposition. Speaking of such, now let's find the solution for the y function. For this, we need y of s equals to delta y over delta, which in this case is delta y. Oh, actually, we first need to calculate that delta y. So let me leave some space for this. So delta y equals to s plus 3 s minus 1. Because we're finding delta y, we're going to replace the y column, the second column, instead of having the coefficients of the system, we're going to replace the second column with the terms to the right of each equation. That'll be, in this case, 1 over s and 1 over s minus 1. So forming the determinant, product along the main diagonal, s plus 3 times 1 over s minus 1 minus 1 over s times s minus 1. Let me rewrite in a nicer way. That'll be s plus 3 over s minus 1. I'm going to leave some space for missing factors. That's plus. What is that? S minus 1 divided by s. So I'm going to multiply the first fraction, the numerator and the denominator of the first fraction by s, and the numerator and denominator of the second fraction by s minus 1. Right? This so we can have a common denominator and combine into a single fraction. S times, that's going to leave us with the product between s times s plus 3 plus s minus 1 times itself, which is s minus 1 quantity squared, everything divided by s times s minus 1. So distributing, that's s squared plus 3s, and plus, I'm going to square the binomial, that's s squared, minus in this case, minus 2s plus 1, everything still divided by s times s minus 1. All right. So actually, wait, I did a mistake on the sign right here. This should be a minus. This also supposed to be a minus. And this is supposed to be a minus. So be careful because the minus affects everything in here. Okay. All right. So let's keep going. So s squared plus 3s minus s squared plus 2s minus 1. Everything divided by s times s minus 1. All right, so that'll be cancel the s squareds. Okay, cancel them. That's going to leave us with 3s plus 2s. That's 5s minus 1 divided by s times s minus 1. Okay, so now we're going to calculate y of s expanded in partial fraction decomposition if necessary, which in fact, spoiler alert, we will need it, and then find the inverse transform. So delta y, which is what we just calculated, that's 5s minus 1 over s times s minus 1 divided by the delta quantity. What's the delta quantity? Let me go back to the previous page. That is 3s minus 1. Okay, so 3 times s minus 1. And I'm going to divide this by 1 just so you can see how we're dividing a fraction by another fraction. And the next step makes more sense. That is 5s minus 1 over s times s minus 1 times 1 over 3 times s minus 1, which will be multiplying across 5. Oh, let me go here. Y of s equals 5s minus 1 divided by 3 times s minus 1 quantity squared. This time I didn't forget about the s, all right? Let me write this down. Okay, so yes, after doing some partial fraction decomposition, which I'm going to skip to make this video short, this should give us the following. Negative 1/3 over s plus 1/3 over s minus 1 plus 4 thirds over s minus 1 quantity squared. Okay, I'll let you verify that. Actually, these were the same numbers I originally did for the previous fraction, which were wrong. Actually, I updated them, so make sure to do so. And again, guys, notice the point where we're doing the partial fraction decomposition. That is, when we're finding y of s, which is the quotient delta y over delta, and the same over here that we did before when we did the quotient delta x over delta. Do not do it before. It's not worth it. Okay, so let's find the inverse of y of s. That's to do what? Okay, that's the inverse negative one. Oh, let me do 1/3 first. Negative 1/3 inverse of 1 over s plus 1/3 inverse of 1 over s minus 1. And again, I would like you to observe the last term. That's a plus 4 thirds inverse transform of 1 over s squared with some shifting at s going to s minus 1. What is that going to constitute? This will constitute a factor of e to the t when we find the inverse of 1 over s squared, just like we did with the previous inverse transform. All right? Okay, so that'll be okay, that's y of t finally. Okay, so that's the second part of the solution. Negative 1/3 times the inverse transform of 1 over s, which is just 1, plus 1/3 the inverse transform of 1 over s minus 1, which is e to the t, okay, plus 4/3 times the inverse transform of 1 over s squared, which is t. But because of the shifting, e to the t, okay, we multiply by a factor of e to the t due to the inverse form of the first translation theorem again. And this is the end of the problem. So here is the solution to the y function, and that's the solution to the x functions because it's again a system with two differential equations and two unknowns. Um, and two unknown functions, a function of x and a function of y. Well, that's we are expecting to obtain two solutions. Now, I would like you to compare the form of this example number two versus what we did in number one. So for number one, just to briefly recap, we solved a system which was very similar to what we did in the eigenvalues and eigenvectors method. That is some column vector containing the derivative of x with respect t and the derivative of y with respect t, and then just constant coefficients for x and y. Right here, for the second example, well, there could be situations in which the derivatives of x and y with respect t may appear both of them in both equations at the same time. Well, that's depending on the on the modeling of the situation you may be doing. And although this could be no, this cannot be solved actually. So this can't be solved using the eigenvalue and eigenvector because of the or at least with what we learn in lecture, we can solve because of the e to the t and that one because of those non-homogeneous terms. So we don't know how to solve non-homogeneous ones. All right. Well, for non-homogeneous, use Laplace transform as for now. All right. So I think this concludes the solution to the last example and also concludes the section.